Okay, so hopefully, okay, so now it's recording. Um, let me, actually, so let me clarify with the staff room and make sure that, oh no, why are you going to the vet? Okay, I'm hopefully recording. If not, it's somebody, Mayhem, are you recording again? And I feel bad for asking about that, but just mainly because Meg is apparently going to the vet. Albert doesn't know as much about the stream thing, and Henry seems to not be online at the moment, or maybe he's just busy right now. I want to I want to get this done as soon as I can, and also like have it be recording. No. Y'all are fine. Like you're. Oh wait. Oh, we're talking about audio stuff. Yeah. Give me just a moment to upload. Let me go ahead and export this and upload it to the thing. Stop that. Oh, God. I'm sorry, y'all are witnessing my absolute utter fail at doing a stream. Oh, God. Exporting. Exporting. I am currently attempting to make this actually usable for people and also doing the thing where I upload the completed PowerPoint at this point to the internet. I forgot to finish up the vocabulary at the end, but I'll deal with that. I'll burn that bridge when I get there. And I really hope my computer doesn't decide to poop out on me right now. Yeah, so if you have if you go to History of Dinosaurs and you go into like the lecture PDF and you just open it, if you're on a browser, it won't download. But I'm uploading it right now, or attempting to upload it right now, so that you all can actually have the updated version. Because I have a crappy version that's already up, but it's not nearly as complete as it should be for actual full use. I just put a version up there so that people would have something to go off of. Okay, yay, Sid is recording. All right. And don't worry, I'm uploading another one that actually has like images and stuff in it, if my computer doesn't freeze up on you. Okay, and I am also hopefully recording because I have the recording and the streaming button up. Publishing. Oh yes, my mountains. This is Rio Arriba County in United States. I forget what this extension is called, but I get like thousands of really pretty Google images to use as my startup thing. Okay, it's publishing. Are you going to finish publishing? Are you going to load? Oh, well. Anyways, I am super sorry about the lateness. I am not great at this entire technology thing. But, you know, it's a learning process. It'll be faster the next time I do it. Now, I don't mind you including the Discord chat. Because, you know, that can be pretty helpful sometimes. Also, by the way, I'm probably not going to respond to the lecture chat once I actually start lecturing unless you yell at me or, like, at me, because I don't want to get too terribly distracted once we get to the actual lecturing. So right now I'm being distracted by the lecture, but don't worry, I've added on a caveat onto my introduction more about me so that y'all are very aware of the kind of person I am. Okay. And I promise this time it's not the internet being slow because my friend has Google Fiber in his household. I just have a computer that's slower than me, and I'm not saying this to be self-deprecating. I actually legitimately have issues with slow processing skills. So, you know, it's just how I am as a person. Okay, I'm going to go ahead and add it onto the original post I made so that I don't have to deal with bull crap soon. But yeah, so I'm uploading the most recent edition of the History of Dinosaurs lecture PDF, mainly because the first one I uploaded was just words and also didn't expand upon a lot of the dinosaurs, because as much as I am teaching a dinosaur class, dinosaurs, like, they're interesting to me, but I don't professionally, like, study them, per se. I'm a rock hound, as you will learn very quickly from my stream here, that I am very much a rock hound. And unlocking my thing. Yes, yes. Oh god, which one is it? That one. It's gonna be that one. Okay. So now the actual file is being uploaded, and after this we will actually get to my lecture. Let's see. Yes, Earth Sciences courses are amazing, and also rock hounds are great. I love rocks. Like, I could talk for hours about rocks, but I'm not going to do that. I'm only going to talk for, at most, 30 minutes about rocks. And minerals, but mostly rocks. Okay. Yes, I do indeed crave that mineral. I crave several minerals. Anyways, okay, so now I'm closing that. So the updated History of Dinosaurs Lecture 2 is up as a PDF now on the classroom. If you want to download it, or if you want to, like, follow along, that isn't that. That's something else. Oh, God. Okay, we're getting to the actual lecture now. Okay, stop that. Nah, you're good, Meg. I totally understand. You're fine. Please don't lick arsenic rocks. I mean... Oh, yeah. Because you can technically lick asbestos rocks and not be as close to dying, but arsenic rocks will actually just straight up kill you. Okay, so now I'm going to at everyone. Lecture is actually starting. No, do not take notes yet. I will let you know when it's time to take notes. Stop it. Okay, everybody. Okay, no more adding everyone. Oh my god. I am so sorry. Okay, so I'm going to set my phone down. At me, I'm going to turn on the sound on my phone so that I can actually hear when somebody yells at me for actual questions. Yes, of course I go into the Homestar Runner theme song. Have you met me? Actually, most of you haven't. This is probably the first time you're interacting with me. So, we are about to begin History of Dinosaurs Lecture 2, The Triassic. I know there's more to the title than just The Triassic, but I'm using the word The Triassic mainly because that's mostly what I'm covering aside from rocks. Lecturer is Blaire. Today is June 28th. It's Thursday. It is now 7:38 p.m. Chicago time, even though my computer says 6:38 because I'm stuck in freaking Utah of all places. Let's go. So, today's class this is that class outline. There's going to be a slightly more detailed introduction of me because I wasn't able to be in the chat when Meg was introducing everybody and to say more about me. And then after I introduce myself for just a brief amount of time, I'm going to go into a basic geology overview. And by basic, I mean it's probably going to be more detailed than what you'll actually need for the class. But Meg is letting me teach this one, and you're going to get a geo overview for the stuff that I usually think about when I think about geology and paleontology at the same time. And then I'm going to very briefly go over how to read a scientific paper and go over Langer 2014, just so that that's fresh in everyone's minds, as we begin talking about the Triassic and briefly introducing the weird archosaurs that were around during the Triassic. And then I'm going to go into the basic dinosaurs of the Triassic. And then I'm going to go into dinosaur groups and more specifically what defines specific dinosaur groups. And then I'm going to explain the Triassic extinction. And then I'm going to talk about the early Jurassic and dinosaur diversification. I guess I'm going to go ahead and check in on the chat and make sure that no one has actually died yet. Okay. All right. Okay. No, I didn't stop talking. I don't think I stopped talking. Anyways. So I will let you know when to start talking or when to start writing down notes. When you see like a big title that says geology, that's when you're going to want to start talking or not talking. Oh my God. Taking notes. And then when the, and also I will say start taking notes now. So not yet. So let's go ahead and briefly introduce me, who sucks at tech. I am a rising junior at the University of Wyoming. I got accepted a couple of weeks ago, and I've officially withdrawn from the University of Rochester, and I'm pretty freaking pumped about it. I've done 3 years at the University of Rochester, but due to like my entire life being a hell mess, I've missed a lot of credits, so I'm technically going to be a junior when I go to Wyoming. I am pursuing a Bachelor's of Science in Geology, which I've said quite a few times. Yay! Welcome to joining UW this fall. We'll probably run into each other. Anyways, I am a big fan of saying hello to people who are also going to my same schools. I have a very big geology focus in terms of how I view science and how I view paleontology in general. I have an extensive background in biology thanks to high school and veterinary classes from high school. From 9th grade to my senior year, I basically did exclusively biology, and 2 years of those science classes involved sticking my hand up cows' butts, making dioramas of reproductive systems, learning how to give shots to animals, figuring out how, learning stuff about agriculture because I was tied in with the FFA. I have a lot of hands-on experience with biology in terms of medical biology. All right, and then while I was at the University of Rochester, I did a lot of workshop and lab leading exercises. Okay, not a lot. I did it once, but before that, I'm like that person in your class that already knows what the teacher is going to say, so I, pseudo do what the teacher does. I'm a really annoying person to actually get to know in real life. I super apologize for that. But, so I have had experience with leading people through workshops and labs in geology. It was the Principles of Geology course that Penny Higgins runs, and I mentioned her next, but so I know how to teach basic geology, basically, is my main teaching experience. I've done field work at Natural Trap Cave. I've done field work in the Uinta Basin, which is in eastern Utah, so near Vernal, but a little south of Vernal, Dinosaur National Monument in the U.S., a little south of there. I've done field work there, and also in the Hanna Basin, which is it's in south central Wyoming with there's the Wind River mountain range on the east side, and there's another mountain range on the west side. I still need to more properly learn those, but I've done field work in geology with Penny Higgins, who is she does mammals from the Cenozoic, and she does a lot of isotopes as well, which is, I talk about that as well. I've worked in labs. I've worked in 2 labs. I've worked in SciReal, which is Stable Isotopes Ratios in the Environment Analytical Laboratory. I've also worked in a Paleomag lab, but that's not super relevant to this discussion. And yeah, also the Uinta Basin is really awesome. Sorry, I'm just checking up on the chat. Stop telling me to join the internet. All right. So, and basically, I've done lab work. That's my other thing. My dream job in paleontology is something involving a museum and some form of public outreach. I really, honestly, I just kind of want to be like Emily Graslie, except for rocks, almost exclusively, but also for other things. But basically, I'm a wannabe Emily Graslie. That is my hope. Stop, this isn't an annoyingness contest. You are all great. Annoyingness is whatever. It's not a good or bad quality. Annoyingness is just what it is. Alright, anyway, so, and then at the bottom I state my various loves, which are spiders, rocks, memes, puns, and JoJo's Bizarre Adventure. If you get me started on any one of those, I will talk for literal hours. That's just kind of what happens. The rock scoop. Me. Alright, so after this slide, you're going to want to all take notes. So all of you should start taking notes in 3, 2, 1. So, when we talk about geology, we are talking about the study of the Earth. So basically, the planet. And more specifically, the rocks. Geology is very important for paleontology because paleontology gets a lot of its specimens and samples from the Earth. Fossils come from the Earth. Dead things go into the Earth and sometimes come out of the Earth. Who knew? So for the purposes of this class, the following concepts are going to be really important to have a very basic understanding of. Those concepts are going to be the rock cycle, how we get rocks, how rocks turn into other rocks, how rocks do the rock thing, basically. You're going to learn about plate tectonics, which is basically how we know where bits of the Earth were at various different points in time. You're also going to want to know about volcanoes, not necessarily because we're volcanologists, but because volcanoes have been pretty important in causing mass extinctions and also contributing to mass extinctions and environmental change that cause big population fluctuations. We're also going to talk about taphonomy, which is the process of a dead thing going from being a dead thing to a fossil. And then we're also going to talk about stratigraphy and dating. Stratigraphy is how we determine what happens when in geologic time, and dating is how we put a specific number, or at least a general age, on those events. If you are more curious about geology and you haven't ever done geology before, or you just want to talk rocks to somebody, feel free to shoot an email to me. You can also hit me up in the office hours that I have after I do my lectures. I'll try and restrict what happens in the office hours to what needs to be covered in the lecture. But otherwise, like, if you email me or if you know my various URLs on Tumblr or something and you shoot me a message, I will do my best to respond in a somewhat timely manner. I'm not always great at this, but I will try. And also, just in general, if you're going into paleontology, or if you're doing anything ever, take a geology course at some point in your life, because geology is super nice. Obligatory pun, because I run a very bad paleontology joke blog. Haha. All right, so geology, the study of the Earth. Let's get into the basics of geology. Let's talk about the rock cycle. So the rock cycle is that really big diagram right there. You don't have to worry about a vast majority of the things on that diagram. Any words that you see on there that look familiar to what is also being said on the slide, care about. But everything else, don't worry. Just don't. So, first, we're going to define what rocks are. And rocks are mineral-based solid material that forms from geologic processes. And from that, we have to define what a mineral is. And a lot of people are probably going to go like, oh my goodness, why do we have to know these things? And the thing is that it's important to know these things because these are what make up the fossils that you dig up from the ground. So, minerals are a chemically formed solid material that have a set chemical structure that forms a crystal lattice. So, some examples of some minerals or mineraloids that people know. Opal is not a mineral because it does not have a set crystal lattice. Neither does amber, neither does obsidian. However, ice is a mineral. Feel free to at me if you want to scream at me. I'm not going to deal with it currently in the chat since I'm trying to lecture, but ice is a mineral by this definition. I've had to fight my brother on this for several hours. It's fun. Anyways, so minerals make up rocks. But rocks, like all rocks are made of minerals, but minerals are not the same as rocks. Minerals make up rocks. It's kind of like how all humans are made of cells, but not all cells are humans. In fact, one cell is not a human. That's basically the dynamic between rocks and minerals. Now, the rock cycle consists of three kinds of rocks. You have igneous rocks, which are formed directly from magma/lava cooling. The difference between magma and lava is whether or not it's above or below the crust. So I usually just say molten rock because they're both molten rock. Some examples of igneous rock are pahuehue, granite, basalt, and lava bombs. Lava bombs are a specific kind of rock that form when big things of molten lava get flung out of a volcano and they cool into like a teardrop shape. It looks really cool. We're not going to talk about it too much though. And pahuehue, if you've looked at any islands on Hawaii, or if you've ever visited any of those islands, is the really pokey black rocks near volcanoes, and pahuehue is the really smooth kind of like chilled syrup stuff. Granite should be most countertops are made of some sort of rock that's frequently called granite. That's usually not granite. It's just basically a really hard igneous rock that's pretty much quote unquote everywhere. I can give more examples at a later point in time, but I'm trying to get through the lecture. And basalt is what the ocean floor is made of. It's black, it's pretty dense. It makes the oceanic crust heavier than the continental crust, which I wasn't going to go into, but I've gone into, so oops. So that's igneous rock. Sedimentary rock is rock formed from small pieces of other rocks becoming chemically stuck together. Some examples of sedimentary rocks are sandstone, shale, limestone, and coquina. Coquina is a kind of sedimentary rock that's basically bunches or, oh no, I spelled coquina wrong. My bad. Oh well, I'll deal with it later. So coquina is basically just shells that are literally stuck together by other bits of shells. It's a pretty cool rock. The reason why sedimentary rock is really important is because that's most of the rock you're going to be dealing with as a paleontologist. Fossils tend to end up in sedimentary rocks. If you have a fossil in an igneous rock, that's pretty significant. And I know there's like one case of a fossil in an igneous rock, but it's super rare. I wouldn't care that much about igneous rocks, honestly. Metamorphic rocks are kind of the same deal with igneous rocks. Metamorphic rocks are formed from geologic processes morphing a rock over time. Usually those factors that weigh into a metamorphic rock are going to be pressure, heat, and time. Some examples of metamorphic rocks include gneiss, marble, slate, and schist. Gneiss is usually like just take any generic rock and you morph it a little bit, and that's gneiss. Marble is specifically metamorphic limestone. Slate is metamorphic shale, and schist is further along in the metamorphic stage to gneiss. So like you can make something kind of gneiss-y and gneiss-like, and then it goes from being gneiss to turning into schist. And then, let's see, is there a... Anyways, again, if people have questions, please at me in the chat so that y'all can be, so that I can at least stop my talking and answer some questions. I'm going to try and have it over here, but it's going to be annoying to have to deal with, to try and keep looking at it while I'm lecturing. So anyways, again, actually legitimately poke me if there are issues. No, popsicles are not rocks. Popsicles are man-made. They are not naturally occurring. Icicles are minerals because they're made of ice, and ice has a set crystal lattice, but popsicles are man-made. They're not naturally occurring. So, I guess the final point of the rock cycle that's kind of sort of important is that all the rocks can turn into each other through various processes illustrated to the left. So, for example, say you have an igneous rock, like a piece of granite, and over geologic time it gets weathered and broken down. You have itty-bitty little pieces of it that end up on a shoreline. Then at some point that shoreline turns into a rock. That is going from igneous to sedimentary. And then say you take that piece of sandstone that is just kind of hanging out there in some rock layers, and then all of a sudden it gets folded and morphed and turned into gneiss. That is a sedimentary rock turning into a metamorphic rock. And then say some other granite rock somewhere is deep inside a mountain and it gets morphed into schist. That is an igneous rock going into a metamorphic rock. And then, of course, metamorphic rock and sedimentary rock can easily be turned into igneous rock by, say, some molten rock coming up, melting the stuff around it, and then later on that molten rock turning into an igneous rock. So all the rocks kind of can feed into each other over geologic time, and it goes for some really cool stuff. Oh crap, I just remembered I forgot an image that I was going to show in here. Oops, oh well, I'll deal with that later. So, that's the rock cycle. The next concept that we're going to be going over is plate tectonics, which is how we know what the Earth looked like. So, over on the top left diagram, we have a cross-section of the Earth. And so we have the crust, which is made up of the, just most of those words on there you don't have to worry about all too much on the upper left. And also on the lower left. Like, honestly, if you see any words that are only showing up in those diagrams, you don't have to pay attention to them. So, with the cross-section of the Earth, we have the crust, which is about, 0 to 100 kilometers thick, depending on where you are. You have the mantle, which is a lot more kilometers thick, about 2,000 kilometers thicker, 2,000 and a half, 2,500 kilometers thicker. And it's made up of different layers of the mantle as well, but we're not going to deal with that since this isn't a geology course. And then you have the outer core, which is liquid compared to everything else. Like, the mantle, to a degree, is solid. The only reason why molten rock is seen as liquid is because of the fact that there isn't pressure. Or, no, of the fact that has gone from being in a higher state of pressure in the mantle to a lower state in the crust. Anyway, so then the outer core is liquid, and it's about like, oh my goodness, that looks to be about a little over 2,000 kilometers thick. And then you have the inner core, which is at the very center, and it's solid. And yeah, that's basically what the Earth looks like. And we know that from earthquake data, but I'm not going to go into that because that's not relevant to this course, really. So back to plate tectonics. So the Earth's crust is made up of plates that move. Jesus Christ! Why did you call me? Who is the University of Utah? Oh my God, I'm gonna cry if that's something else. Okay. So Mothswell, I missed the first part of the lecture. What will I have to do about that? We will hopefully have a recording of this lecture up so that you can watch it again and watch me utterly fail at technology. And then after that, you can, and then we also have the notes on the lecture. And if you have any questions from the lecture notes, feel free to like shoot me an email or check out the office hours that I will have after this class, and I will explain some questions. Anyways, yeah, let's see. So where the heck was I before JoJo tried to call me? I'll deal with that later. Okay, so plate tectonics. So the Earth's crust is made up of plates that move around due to processes in the mantle. So there's a bunch of hypotheses for why this happens. The main theory that most geologists will tell you right now is that convection, which is the movement of hot fluid-like things moving through space, pushes new hot magma to rifting plate boundaries, causing divergence. So basically, hot stuff tends to rise, and so when stuff gets really hot down closer to the core of the closer to the outer core of the Earth, the molten rock that is there will push itself up towards the cooler part of the mantle, and in weak spots of plate boundaries, sometimes that lava will come up and push the plates further apart and make more plate stuff. So that is called plate rifting, and it's also, so that is called divergence, and the actual word for that specific motion is called rifting. Sorry, I just mixed up a lot of words there. But basically, divergence is the actual separation of plates. Rifting is the actual process of the magma coming up and pushing the plates farther apart. On the other side of the plate, plates crash together and the heavier plate subducts under the lighter one, which is known as convergence. So again, subduction is one plate going underneath another one. Convergence is the general process of that. Sometimes plates will slide together. It doesn't really, there is a word for it. It's called it's called a transform plate boundary. It's not really a word you have to worry about for this course, so I didn't include it. Unless you want to learn about earthquakes, and you do want to care about it, but we're not learning about earthquakes in this class, so we'll deal with that later. So plate tectonics, I'm so good at words. Plate tectonics, combined with the fossil record, inform us of where plates have been in the geologic past. So, on to the next slide. Vaguely related to plate tectonics, we're going to talk about volcanoes. Volcanoes form usually at plate boundaries. They are outlets for high-pressure molten rock, often found at plate boundaries or near weak spots in the crust. Examples of these kinds of volcanoes found at plate boundaries would be like Mount Rainier and Mount St. Helens, because they are right near a convergent plate boundary, and there's a lot of high pressure magma there, and they just kind of want to poof. They're basically big planet pimples are what volcanoes are. Okay, not big. They're like size ratio the same as human pimples to a human. So volcanoes are essentially rock pimples. They have high pressure magma that wants to get out, and when they have enough pressure to come out, they will come out. Why is that flashing green? Oh, okay, that's somebody else. So, yes, not big planet nipples, big planet pimples. Did I say nipples? I'm so sorry. I meant pimples. Yes, Earth has acne. So, high pressure pimples. And also sometimes, like, there you will have what are known as hotspots, which is basically weaker places in the crust where magma is more likely to break through and create volcanoes. An example of this is Yellowstone. Yellowstone is a hotspot. The islands of Hawaii are also hotspots. Kilauea is active right now because it is a hotspot and there was too much magma inside of its magma chamber and it was like, oh, it's time to pop, and it popped. So the reason why we talk about volcanoes when it comes to paleontology is because they're super devastating to life. And the reasons why they're so devastating is that they are really, really hot. Like, they're just super hot. Any life nearby, like lava or like molten rock in general, is gonna feel the heat. It's like putting a peep next to a campfire. It's not fun. It kills things. Volcanoes are also really fast due to the pressure differential. So oftentimes a lot of times the reasons why these eruptions happen is that there is a whole ton of pressure within the magma chamber, within the earth pimple. And it's super, super high. And it's kind of like those times when you scratch against your skin and you accidentally like scrape off just a little bit of stuff there. And then all of a sudden the pimple just gushes. That's kind of what happens with volcanoes. Frequently the factor that will actually happen is that there's just too much pressure inside the magma chamber for the surrounding rock to handle anymore. One crack will form, and then all of a sudden you have high pressure stuff wanting to go to a place with much, much, much less pressure. It's a common theme in pretty much all of science, that if you have a high concentration of something, it wants to go to a place where there's not that much of the thing in order to create equilibrium. So that's why things like that's part of why things like pyroclastic flows and lava flows are so freaking fast. It's because the magma is just like, I want to get out of here. It's crowded, I want to go to where it's not crowded, and it'll go as fast as it physically can in order to get there. It's why you can't outrun a pyroclastic flow, no matter what Jurassic World says. Yells. Just yelling. Okay, back to the lecture. So, we've covered that they're really hot, they're really fast, and they're really noxious. There's a lot of gases produced in magma chambers that are pretty toxic. Like, there's sulfur, there's methane, there's carbon dioxide. And when magma chambers burst and when volcanoes erupt, all that gas will go everywhere and kill a lot of things, especially if they're nearby and if they're really sensitive. Like, it's just a bad time. And then there's also climate effects that come with volcanic eruptions, especially when you have volcanoes who produce a lot of ash. Those ash clouds can produce similar effects to nuclear winter, which is where they block out the sun in the surrounding area and plant life dies. I think there was the volcano in Iceland. I think it was called Reykjavik. And when it erupted, like, airspace in that area, in like the surrounding 300 to 400 mile radius was just shut off because trying to fly through the ash was immense, and it got super cold over there because there wasn't as much sunshine. And there's also the fact that the release of CO2 can greatly increase greenhouse gas effects within the area surrounding the volcanic eruption. Who's breaking into the house? Probably not anyone actually breaking into the house. Oh, just kidding. That's the capital of Iceland. I don't remember what the name of the volcano in Iceland was, but it erupted about 5 years ago, and there was a big hullabaloo about making sure that nobody flew over it because it was bad. Nobody is actually breaking into the house. It's the friend who's letting me record stuff. Nick, he might come in here and harass me a little bit. Maybe. So volcanoes, they're just super deadly, and they've actually contributed a lot to the extinctions in the past. Like the Permo-Triassic, as Meg mentioned, there was the potential for volcanic stuff to have been involved in there. And as we will learn, it's highly possible that the Triassic extinction was due to volcanic activity. But I'm getting ahead of myself. The next slide is going to be, the Siberian traps, which I thought I was getting ahead of myself, but I'm not. So these are the Siberian traps, which Meg, I think, mentioned in her lecture on Monday. Basically, and these are all words in Russian, so don't worry about them. Basically, what happened is that during the end of the Triassic, there was, oh no, not the end of the Triassic, at the end of the Permian, there was a lot of volcanic activity up in what is now Siberia. And in fact, it looks like a good third of Siberia and Russia in general is covered in these pyroclastic flows and ash beds and just lava flows from that time period, and was a huge factor in why 95% of all life on the planet died at the end of the Permian. So, moving on from volcanoes, we're going to talk about what in the world fossils are. Fossils are remains or impressions of prehistoric life preserved by geological processes. Fossils can include unmodified material, but it is often geologically reworked or modified by geological processes. There are very, so when I was working at one of my field sites, we were working with, Pleistocene and Holocene era fossils and bones. And I asked someone, hey, so do these count as fossils or not? And one of the researchers I was working with was like, they look super lifelike, but they have started to be reworked by geological processes while sitting in this cave, so they are technically fossils. Wait, no, okay, I just checked the Discord chat and someone said Deca. I didn't say no. So Deccan traps happen at the end of the Cretaceous. What I was talking about were the Siberian traps, I'm pretty sure. If I said Deccan traps, feel free to slap me in the face if you all ever see me in the real world. Okay. No, I'm not going to try pronouncing the volcano name because I know I would fail at it. I also know that I'm going to get yelled at. I'm going to get yelled at for mispronunciations all throughout the lecture. So, yes. Anyways, where the heck am I? Yeah. No, the Decans are not at the Permian. The Siberian traps are at the Permian. Decans happen at the end of the Cretaceous. But it's okay to make mistakes and ask questions, because honestly, before I took a geology class, I would have been like, aren't those all the same thing? Aren't, lava traps all the same thing that happened at the same time? I was young and foolish. Anyways, so back to fossils. So fossils are remains or impressions of prehistoric life preserved by geological processes. They can include unmodified material, but is often geologically reworked / modified by geological processes. There are many kinds of fossils, but the first one that I'm going to talk about is going to be the main one that we will discuss in this class, and that will be most relevant to the material in this class. So, we have body fossils, which are fossils that were once part of the body of a living organism. Some examples of this include bone, shells, carbon imprints of animals that were just super compressed and left behind a carbon imprint, and casts, which kind of happen when an organism decomposes but leaves a gap behind for other rock to come in and fill it in. And so some fossils that we have are just literally casts of the space where a dead thing was. Those are body fossils. Those are the main fossils you're going to be worrying about in this class. The next fossils are trace fossils. They are fossils that preserve evidence of life without actually preserving biological material a vast majority of the time. Some examples of this are things like trackways, teeth marks on other fossils. So if you have, say, a bone of an herbivore that has teeth marks on it, the teeth marks are evidence of a carnivore that tried to eat it. Whether or not it was successful is up for debate, but, I let the ichthyopaleontologists deal with those. And then we have burrows, which are basically big holes that used to have a living thing inside of them, but instead of preserving the living thing, the hole that it lived in was preserved. There's actually this really, there was an episode, I think Eons did it, not Eons, it was another YouTube channel that had an episode about these big, huge stone spirals. And people were like, what the heck are these? And someone was like, oh yeah, a prehistoric beaver dug these burrows and they lived inside of them. They were pretty cool. I don't remember the words off the top of my head. I highly doubt it'll ever become relevant, but I'll see if I can find that material at some point in the future and share it with you all, because I'm all about finding cool geology things and sharing them with people. So those are trace fossils. And then we have coprolites, which is fossilized poop. These are specific to animals. Coprolites are slightly more relevant than trace fossils, but I put them lower on the list of importance, mainly because in terms of all geology, coprolites and paleontology in general, coprolites are very, very specific to animals. And it's unfortunate in paleontology that we focus a lot on the animals, because apparently nobody cares about plants or protists or single-celled organisms, which we probably have somewhat more evidence for than animals. Like, it's easier to preserve those things, depending on the organism. And then the last type that we have that is honestly not really relevant much at all to this course, but was something that I learned that I find particularly interesting, is that there are chemical/molecular fossils, which are fossils that preserve evidence of metabolic processes or the environment. Some examples of these would be hydrocarbons and very specific molecules that you can find in fossils, isotope ratios that can be found in certain rock layers and in teeth, and also stromatolites are technically chemical molecular fossils. For people who don't know what stromatolites are, basically imagine the algal beds that you see in lakes that have a bunch of algae and bacteria in them. Stromatolites are fossilized versions of those. They kind of look like big sedimentary rocks, but the reason why we know they're stromatolites is because they usually have a very specific shape and very specific kinds of layering involved in them. Now, let me see. Now, I'm going to momentarily check on the chat to make sure things are okay. Yep, everything looks okay so far. Also, yay! Thank you, BWiz, for posting the Untangling the Devil's Corkscrew. I thought it was eons. I just wasn't entirely sure. But anyways, so those are fossils. And here are some images of fossils. This is the part where if you're not looking at the stream, you're going to want to look at the stream. So, in the upper left-hand corner, we have some sort of small lizard, most likely a gecko or a chameleon, stuck in amber. Amber is also a way that we can get fossils. I didn't label that on, I didn't put that on there, but amberization slash being encased in ice is a way to get fossilized. We also, on the other upper right-hand corner, we have some coral. On the lower left-hand corner, we have an ammonite. In the middle, we have a cast of some sort of gastropod, ambiguous gastropod number 2467. And then in the lower right-hand corner, we have a piece of petrified wood. And I guess I didn't... Oh, I know what I did. I put the slide in the wrong place. Oh, well, I'll come back to this slide after I talk about taphonomy, which is how we get fossils. How do we make fossils? The first part of getting fossilized is that you get dead. And this happens to 100%/70%, 75% of the organism, depending upon whether or not an animal was partially eaten before it actually died. Organism dies and experiences pre-burial scavenging and decomposition. The vast majority of soft tissue gets lost at this point. So the reason why we don't have a lot of soft tissue is mainly because before we even get to the other steps in fossilization, usually an animal dies and gets eaten by decomposers, whether that be scavenging animals or worms or maggots or other bacteria and stuff like that. You know, like basically most of the organism that is soft tissue goes away. And then the thing gets buried, which is about 75 to 50% of the organism survives the burial process, which is when sediment covers up the parts that didn't end up getting decomposed. But the best environments for doing this involve low velocity water due to quick burial that tends to keep everything together. So, like, if you have a really fast rushing river, you're not, like, you'll get buried, but your entire rest of your body is going to be spread across however far it took you from where you initially died to where the last part of you got buried. And also, you're going to have, and also depending on the environment, if you're too warm, the decomposition process goes faster, and so there will be less of you to get buried. So some examples of good places to get buried in are marshes, but not super warm marshes. Don't get buried in Florida if you want to get fossilized. You're going to decompose before you get fossilized. Stream beds, very low velocity stream beds, and the ocean. A lot of the fossils we have are marine because the ocean is a really good place to get fossilized. Some exceptions to this very specific rule of getting buried in low velocity water are deserts. We have quite a few fossils that were buried in sand dunes. We have ice and we have amber. Those are really good places to get buried and preserved. Then step 3 is the thing gets diagenized. Diagenesis is the process of making rock. It's a geochemical event that turns not rock into rock by forming groups of crystal lattices. The fossils present, the present biomaterials in the thing that's getting fossilized will likely get replaced, recrystallized, or permineralized, which means that the gaps within the organism get filled by other rocks, while the surrounding sediments solidify into rocks. So replacement of existing biominerals just means that, say you have a bone that has apatite in it. In fact, most bones have apatite in them. It's very rare to come across a bone that doesn't have apatite in it, and if you do, you've got a problem. Anyways, so apatite in a bone. In replacement, that apatite gets taken out and some other mineral gets put back in. Sometimes that's going to be pyrite, other times that's going to be opal, even though it's a mineraloid, not a mineral, but that's for a different time. Recrystallize means that the biomineral that's already there just gets turned into something else. So take apatite, for example. There are 4 different types of apatite, and usually what happens is that you'll go from the one type of apatite that you use in a living body to a more geologically stable form of apatite. So it'll just change a little bit, and it won't change itself entirely. And then permineralization, again, as I said, is when gaps are filled in by whatever minerals are forming within the surrounding rocks. So after you get diagenized, you wait for a while. You wait for a long while, and both diagenization and waiting usually ends up taking about 50 to 15% of the organism left, depending on what happened during decomposition and getting buried. And during the waiting process, you just wait for a very long time. Sometimes in the process of waiting, the fossil will get metamorphosed. There's a really cool image of a trilobite that got twisted and sort of slanted by metamorphic processes happening to the rock around it. Sometimes we come across these fossils, and it's definitely, if you're into doing field work and doing the actual digging up of fossils and cleaning them and stuff like that, that's a really important thing to know. And also, if you're interpreting fossils, it's really important to be aware of any potential metamorphic processes, because you could have a bone that looks really funky, but the only reason why it looks that funky is because it got metamorphosed while it was waiting to be exposed, which is the last step in taphonomy. Exposure rarely ever means discovered. Sadly, a vast majority of the fossils that we have make up less than 10% of the presumed life material of the organism, including soft tissue. And usually, when a fossil gets exposed, it's going to erode and weather away very, very quickly. Because fossils are not the same, they are not made of the same things as the rock around them. They're partially made of the same things, but they're also just super fragile because they were made from a living organism that should have decomposed back when it first died. Because of that, it is much more likely to weather away faster than the rocks surrounding it. So you can have a piece of sandstone that has a Tyrannosaurus vertebrae in it, and when the vertebra gets exposed, it's more likely to disappear within a short amount of time compared to the rest of the rock. It's very fortunate if you find, there are stories in which people have been oh, look, that's a fossil. I'm literally on the last hour of my field trip. I'm going to mark this spot and hope that fossil is still there when I get back. And when they get back, the fossil will still be there, but it'll be half gone because of how fragile fossils are. So I'm going to go ahead and go back up a slide to number 10, and I'm going to say, and then I'm going to talk a little bit about, okay, so Jay said that bone is hydroxylapatite, correct? And I totally messed up the phrasing of that, but I believe that's the one. It could also be fluorapatite. I will have to look that up more specifically, but that's not super crucial to the lecture. And on opal fossils, yes, opal fossils are really cool. They are very specific to Australia, mainly because of the fact that Australia is just weird in a lot of different geological ways. They're also very pretty. They're pretty rare, again, because you have to be in Australia. And that is that's that. So back to the slides. I'm back on the image I was talking about a little bit earlier before I started talking about taphonomy, and I'm going to talk about all the different stages of these fossils. So the amber fossil, that's an amber fossil. Amber is basically when you have tree sap and then over geologic times it turns into amber. I'm not entirely sure of the process on that. Amber is in the same class of like mineraloids that opal is, and the main thing for the reason why opal and amber don't qualify as minerals is because they don't have a set crystalline structure. Like you can't, like if you go down to the individual microscopic scale of one molecule of amber or opal, you're not going to have something that will be able to repeat itself over and over again. They're too fluid to really be proper minerals. But that's just amber. So then on the upper right, we have a permineralized piece of coral. So the coral itself is kind of like the lighter stuff that you see in the fossil, and then the darker stuff is from the surrounding rock that fossilized with it and filled in all those gaps on the coral. And then in the lower left-hand corner, we have a ammonite that has been pyritized. So what has happened to it is that a lot of the calcite that was making up that shell got turned into pyrite over geologic time and during the process of diagenesis. Usually that means that a lot of iron and sulfur came in and took out the calcite through the groundwater that was making the rest of the rocks around it the rock, and turned that fossil from it being a calcite shell into a pyritized fossil. And then right next to that we have an ambiguous shell that's a cast. The reason why you can tell this is a cast is because it's got the inside of the shell instead of the outside of the shell. So you get a pretty good, especially with invertebrates, you get a pretty good sense of what the interior of an animal looked like through casts. For the reverse process where you get the outside of the space of the thing that exists, that's called a mold. Again, so those are called cast and mold fossils, especially when you have two of them together. And then we have a little piece of petrified wood here, and I'm using petrified wood as an example of replacement, because petrified wood, before it turns into petrified wood, is just wood. And then when it's buried and when it goes through the fossilization and taphonomy process, all of that wood gets replaced with quartz. That's what petrified wood is. It's just quartz that looks like wood. That's why it's so heavy. It's because it's quartz. And then there are also other kinds of minerals that can replace wood as well. This happens a lot with wood, mainly because wood is just a weird molecule and things like to fill into wood, because wood has a lot of spaces for water molecules and for water molecules to deposit things that aren't water molecules. So that's why petrified wood is the way it is. So that was taphonomy. And then after taphonomy, we're going to talk about stratigraphy, which is layers of time. Stratigraphy is basically sequence of rocks and events recorded by the geologic record. And the way that we can tell what happens in a sequence of rocks is by using what's known as Steno's law. So as a geologist, his last name was Steno. He came up with some laws, and other people added on more laws afterwards. But basically, it's used to determine the relative age of rocks and the order in which rocks happened. So the first of Steno's laws is superposition, which is basically that oldest rocks are at the bottom and / lowest part of the record, and that works because gravity, and just like, you know, if you make Jell-O and you put in your first red layer of Jell-O, that's going to be the oldest layer of Jell-O you have. You're not going to put in a red layer of Jell-O and then it's going to suddenly be at the top of the Jell-O unless you flip the Jell-O over. That's something that does happen, but that's for geologists to figure out. That's not in the scope of this course. Anyway, so that's superposition. The second rule is original horizontality, and everything starts out horizontal thanks to gravity. Changes in this indicate geologic events after the formation of the rock. The one exception to this is when you have a hunk of igneous rock that's just kind of sitting there, and then it's in the ocean, and the ocean surrounds it with a bunch of sediments. Sometimes that happens, sometimes it doesn't. It really kind of depends on the scenario, and also when you're looking at a situation like that, you also want to look out for, was this igneous rock there before the layers formed around it, or did the igneous rock intrude in? But that's not in the scope of this class. So Moving on. The third part is lateral continuity, and that is that rock layers will stay the same on either/all sides of a gap in the rock. So for example, the Grand Canyon. The Grand Canyon doesn't have one stratigraphy happening on the other side and then the big gap of air and erosion and then just a whole nother rock record on the other side. You can look at the beds and go like, oh yes, that big chunk of limestone is on the north side, and then through the gap you can see that it continues on the south side. That's lateral continuity in work. And also I just love the Grand Canyon, so I'll probably talk at least a little bit about the Grand Canyon because I love the Grand Canyon so much. So those are the original 3 rules for Steno's laws. And then added on to Steno's laws are 2 specific rules. There's cross-cutting relationships, which is that cuts across rock, which can be canyons, they can be dikes, which are specific igneous intrusions. There can be faults, which is, you know, when the rock faults and you get earthquakes and stuff. And then more igneous intrusions. Those cuts across the rock are going to be younger than pre-existing rock. So if you again, back to our jello example, you have a layer of jello and you cut across it and then you shift the jello a bit. That cut across the jello is younger than the jello actually forming. And then the last one is going to be faunal succession, which is using index fossils, which are specific fossils that are very specific to a time period, to date rock layers to that specific time period. So for example, if you have a Tyrannosaurus in a layer of rock, that rock is from the late Cretaceous. And if it's not from the late Cretaceous, then you've either got a very significant discovery or you're reading something wrong. That specific process of using fossils to date layers and correlating those layers together is called biostratigraphy, which is pretty important in paleontology. And then the final thing to deal with stratigraphy on a basic level is the concept of unconformities, which are gaps in the rock record caused by erosion, but they're not the biggest thing to worry about with regards to this class. Like, I can't think of anything within our lectures that would involve talking about unconformities to a great extent. So on the left-hand side of this slide, you will see a big, huge thing that is actually the stratigraphy of the Grand Canyon. Along the bottom here, you've got the little Colorado River and some dark rock, and then you have some more slanty rocks, and then suddenly there's like a line, which is called the Gray Unconformity. And then above that, you have all of these Paleozoic rocks for years and years on end. So that's just a very basic example of one of the greatest and easiest to deal with examples of stratigraphy. And then from that, we're going to talk about dating. Dating can be divided. So dating is basically how do we know how old rocks are? We have 2 different kinds of dating. We have relative dating and absolute dating. Relative dating tells geologists which events happened in which order. And it's best told through stratigraphy and doesn't change much at all whatsoever. A good example of this is the geologic time scale. The Cretaceous is always going to be more recent than the Jurassic, which is always going to be more recent than the Triassic. No amount of anything is going to really change that order because that's just how the rocks lay. The only time in which that looks different is if you have had a bunch of folding that literally makes the beds turn upside down, and then in that case that's not a change in relative dating, that's just the rocks being really funky, really stinking weird. Sorry, I've been really good about not swearing too much during the actual lecture. Okay, so that's relative dating. Then absolute dating is when we place a numerical age on a rock or fossil, and this number is more likely to change due to advancing techniques in the way that we date things. A good example of this one is that the end Cretaceous used to be 65 million years ago when I was like 5 or 10. Like, I think it wasn't really until like about 10 years ago that they started to be more open about the fact that like, oh, the end Cretaceous is actually 66 million years ago. And the way that we do absolute dating is usually through radiometric dating, and that uses radioactive isotopes and decomposition of those radioactive isotopes to determine the absolute age of something thanks to the half-lives of radioactive isotopes. So basically, every radioactive isotope has like an amount of time that it'll go through before it turns into a more stable form. So a really common one is the unstable form of uranium will turn into lead over however much time that takes. And one important thing to note is that a lot of times people will talk about, like, especially people who don't really get into paleontology will be like, oh yeah, this thing was carbon dated to this time and stuff like that. And carbon dating is really useful for archaeology, which is much more recent, but it only really works up to about 400,000 years ago because the half-life of carbon is fairly short, and also carbon is just a fairly small molecule. Anytime further back than that is usually going to involve lead, and then lead uranium, and then helium and argon, and many other forms of radiometric dating measurements. So that's the dating stuff, and that's actually pretty much all that I'm covering with regards to geology. And now we're going to move on to how to read a scientific paper, which this is just a brief summary of what I gave to you all right before we were like, oh, by the way, read a scientific paper for this class. These are things I learned from my paleontology professor at the University of Rochester. And even though I somewhat knew how to read papers at that point in time, like, the tips that she gave me helped me read them faster and get to the basics more so. So basically, I'm just going to go over what I saw in the paper, kind of very basic. This is like just, the basics of what you should get when you read a paper. So we're going to start with the abstract, and the abstract gives a very brief description of the question of the paper. And so within this abstract, I saw three questions that were asked, which were, how were basal dinosaurs related to each other, and where did they come from? And why don't we still have an answer to that first question? And was the rise of dinosaurs rapid or gradual? A good abstract will propose questions and leave you with only one to continue thinking about when you go through the rest of the paper, which this paper did. It answered the first question, which was, how are basal dinosaurs related to each other, and where did they come from? So where they came from is that this paper points that, or the abstract itself says that the fossils point towards southwestern Pangaea, which would be modern South America, Africa, and India. And the last question, which is was the rise of dinosaurs rapid or gradual, it implies that there is a more gradual rise to dinosaurs. So the only question it leaves for you to think about through the rest of the paper is, why don't we still have an answer to the question of how basal dinosaurs were related to each other? So we've got the abstract, introduces the basic question that you should think about. Then I tell you to jump to the conclusion, because the conclusion gives basically what the answer to that question is and the impacts on those conclusions from the questions. And in this paper, that section was titled Conclusions, Directions for Future Work, but I'm only using the last paragraph as the image here, mainly because that's like the sum of it, because even within the conclusion, you'll usually have the very last parts of discussion happening. So the question was, why don't we still have an answer to the question of basal dinosaur evolution? And the answer that they provided was that there is a lack of non-contentious data points. And I personally think that this is due to preservational bias, but that's due to my background as a geologist. I'm pretty sure Meg probably has a slightly different answer, though it probably falls along the lines of preservational bias. And half of the art of paper reading involves letting yourself think about and make connections to things you already know. When you read a paper, half of it is a matter of learning basically what is going on in the paper, and then also being able to take your knowledge and put it into your understanding of that paper. So when I'm going through the paper, I'm usually using a lot of knowledge I already know and a lot of assumptions I already know. And it's always good to check these assumptions with people, especially when it sounds super weird or super like, oh my gosh, why hasn't anyone else thought of this? And the answer is probably, maybe they haven't, but oftentimes they have, and it wasn't one that worked out. So, continuing on, there's strong implication that this question of why don't we still have an answer to the question of basal dinosaur evolution could be answered in the future by other research groups and with further data collection. So that's basically what this paper is saying is, we don't have an answer to this question because we don't have enough data. Let's go get some more data, guys. Woo! So then at the very bottom, there's some bonus acknowledgments to some pretty cool people. I've personally met Scott Hartman. He's the one that does a lot of the skeletals that all of us paleo artists like to use. He's an absolute sweetheart in real life. And Smith and Brissett, which are also mentioned in this paper, seem pretty good at what they do. So, They're people. They exist. They do science. They seem pretty chill. And then I'm going to go ahead and move on to the introduction. So the introduction gives more information about the background behind the question being asked. And as a reminder, that question is, why don't we still have an answer to the question of basal dinosaur evolution? The introduction is titled Early Dinosaur Systematics, Definition, and Controversies. Most of these papers aren't going to say, this is the introduction, or this is the results and methods, or these are the data points, or this is the discussion, or whatever. They're going to have these big kind of blocky words. And it's something that you learn over time as you practice with papers, but it's a pretty common rule of thumb that the introduction will always directly follow the abstract. So, the introduction illustrates differences and difficulties in defining a clade by traits or relationships, which, if you take a look at my notes, which you may or may not be doing, I do make a comment saying that, like, translating technical speak into something more readable for me, which is that phylogenies and taxonomies determined only by unique traits is going to be less useful than using relationships based on similar traits. Phylogenies and taxonomy based purely on naming falls into the fault of being defined by what a named clade can include by definition agreed on by the scientific community. So it's complicated to try and deal with these older taxa while using more modern ways of making connections with each of families, mainly because they were formed in two completely different time periods and also with different intentions. And then the basic point of the introduction should be that it should explain why the question is indeed a question, which Langer does really well, and as the highlighted points figure, and as for me, when I use highlighting, part of it is to highlight important things, and the other part is to just break up text. I will frequently just stripe my papers with highlighting in order to make it easier for me to break up the information that's being said. So I'll break up really long paragraphs into like 1, 2, 3, 4, like 5, 6 mini paragraphs in order to make it easier for me to read with highlighting. So that's the introduction. And then discussion. I'm not going to talk too much about discussion, mainly because it is a bunch of legwork for the science and discussion happening within the paper itself. Everyone will get a different thing out of the discussion from other people. And thankfully, a vast majority of the Langer 2014 paper is made up of entirely discussion, and I'm realizing my Discord chat is probably yelling at me right now. Nope, not yet. Okay, just kidding. Okay, I'm going to clear out that notification because it looks a lot like my Discord notification. So we're good. So, basically, I also personally argue that the small subsections within what should be the introduction fall within discussion due to their content and how in-depth they go. And so the discussion, the basic points from the discussion that come up in a very basic summation of the 3 to 4 pages of discussion is that the history of current data is displayed, and it shows the different species and why the species do what they do or why they don't work for setting up certain phylogenies and why they do or don't support specific proposals that people have put up. There talks about the controversy surrounding specific data points, and it also tells us what is known and what can be inferred from that. For me, what I found particularly interesting was big word paleogeographical distribution of dinosaur-morph records, which is basically this is where the fossils were, and this is likely where dinosaurs originated from. This relies on the use of stratigraphy to get an understanding of the spread of dinosaurs during the Triassic. And a vast majority of the times in paleontological papers, what will catch my eye is geological things. And so that's going to be completely different from Meg, who will probably look at a paper and want to understand the evolutionary arguments being made. And so that's so basically every single person comes to a paper with their own understanding and knowledge, and they'll get something else from it. So it's okay if you read a paper and you compare what you think about it to somebody else, and they come up with something that's essentially the same but done in a different way. You're not thinking badly. You're not thinking wrongly. You're thinking in the way that makes sense to you. So, and it's important to understand that, and it's also important to accept, acknowledge, and appreciate that because, so say Meg and I were to sit down and talk about this paper, she would be able to explain to me the things that I just kind of was like, oh, that seems cool. I don't really have the brain space to understand what that means right now, but that seems really cool. And I can explain to her why the things that I care a lot about and get really excited about with this paper are so important and exciting. So that kind of ability to have your own take on the paper and not be as worried about whether or not your take is wrong just because you differ on one point or focused on one thing is super chill. So then the final part of this is that I'm just going to talk about some words I didn't know and words that you might not know that came up while I was reading the paper. And I was like, some people probably don't know these words. So one of them was homoplastic, which is basically saying that the similarities between organisms that were not inherited from a common ancestor. So convergent features or reversals. So a good example of this would be like having wings is homoplastic between pterosaurs, modern birds, and bats. They're not related to each other except very basally, like way, way, way far back into like the Permian, but those traits are unique among them particularly and make them somewhat similar. Then plesiomorphy is a cladistics term used to describe the lack of a derived character or trait in a specimen. It's probably not something you're going to run across unless you want to join the hell space that is dealing with cladistics and phylogenetic trees to an extensive amount. It's a mess. It's a fun mess, but it's a mess. So don't worry too much about that one. And then this was one that actually came up in the Discord chat at one point, which was non-Eusauricians. And I broke it down into parts, and then I realized I had it slightly off a little bit. So I've corrected that here. So non is not, and then Eusauricians are the group that unifies theropods and sauropodomorphs as sauricians. So non-Eusauricians are sauricians that are not within the common, more derived groupings of Saurischia, which, depending on who you talk to, applies to all basal sauricians like Eoraptor, since they don't qualify as theropods or sauropodomorphs, depending on who you talk to. Another word that was just kind of like that's a big word, I probably should know this word, but I don't know it, is vicissitudes, which is basically a change of circumstance or fortune, typically one that is unwelcome or pleasant. And in this paper, it was used to refer to the fact that, oh yes, science is advancing, but the ways in which it's advancing is not actually helping paleontology or this specific question. And it sucks, because I wish it did. That's basically what it meant. And then the last kind of group of verbs has to do with taxonomy. So alpha taxonomy was used in this paper to refer to the naming of a species. And alpha taxonomy is the discipline of detecting, describing, and classifying new species, as well as revising the classification of previously described species. There's some more related words I put below that, but they're not super crucial, and I know I'm taking a long time, so I'm going to go ahead and move on from the paper part of my lecture onto the Triassic, which was from 252 million years ago to 201 million years ago. There were some weird archosaurs, and there were some pretty generic dinosaurs. So, setting the stage for the Triassic. At the end of the Permian extinction, there was like around 95% of all life on the planet, which was 96% of terrestrial life and 70% of marine life, give or take, went extinct. And there were suddenly unfilled niches everywhere. The climate at the time was dry and warm, but fairly unpredictable, as shown by a paper by Whiteside in 2015. I'll upload that at some point. It's a fairly interesting paper if you're interested in the Triassic at all. Like, super cool paper. And then, during this time, reptiles diversified, most specifically crocodile archosaurs. So, from last lecture, you probably remember this image vaguely, which is basically Archosauria and the two different main branches on it. You have Aviometatarsalia, which is the bird-line archosaurs, which includes, at this point in time, Pterosauria and all dinosaurs, including birds. Then, on the other side, you have Pseudosuchia, which includes crocodiles and all things that are more related to crocodiles from that point onward. So Pseudosuchia is the crocodile line archosaurs, and there's a bunch of groups within them. I'm just going to briefly go over them. There's Atosaurs. They kind of look like they're kind of like Tankosaurs, but they're more spiky. They look super weird and interesting. They look like a xylophone that you could play. It's pretty cool. Poposaurs, they're also croc line. The most common one that most people will probably know off the top of their head are Rauisuchians, which basically look like reptile dogs with kind of T-Rex looking like heads. This one right here is Prestosuchus from the American Museum of Natural History. Then there's Ornithosuchidae, which I don't know super well. They're relatives to crocs. And then we have Crocodilomorpha, which is where crocodiles are. So that's Pseudosuchia. And Why didn't dinosaurs diversify during the Triassic? Well, there's kind of a few factors going on here. We have competition, which is that there were all of these archosaurs and other reptiles that were in competition with each other. And usually the first group to fulfill a particular kind of niche will be the one that will prevail until there is a fluctuation in the population for whatever reason. The only exception to this is when there is extenuating circumstances involving environmental and ecological fluctuation within a group. And so that's competition. And then the environment of the Triassic was not super ideal for dinosaurs. The climate was very arid, but also fluctuated a lot as a result of the Permo-Triassic extinction right before it. And instability in an environment restricted the dinosaurs' ability to maintain non-generic lineages. And so some of you are probably going, okay, so that's true for dinosaurs. Why didn't that work for, like, all the other pseudoseuchians? Like, you would assume that they would have been able that they would have also suffered from becoming more specific and becoming more diversified instead of just saying generic. And honestly, the last part of it is luck or lack of it. Dinosaurs just didn't fill those niches in time to actually become extremely diverse other than their generic forms that existed in the Triassic. They didn't establish themselves in those niches before the other dinosaurs did. Not dinosaurs, oh my gosh, before the other archosaurs did. And so they didn't diversify into those spaces and stayed mostly generic during that time period. Let's see. Has there been any ads? Okay, not yet. So that's why dinosaurs didn't diversify during the Triassic. So going into the Triassic, dinosaurs. As we defined in Meg's lecture, dinosaurs are the most recent common... Dinosaurs encompass the most recent common ancestor between sauropodomorphs, theropods, and ornithischians, and all of their descendants. And so you're probably wondering, what exactly are the differences between all of these groups? So I'm going to begin by discussing hip anatomy. We're going to talk about hip bones because understanding the hip bone structure helps us in defining which dinosaurs go where. So hip bones hips in total consist of 3 specific bones. There's the ilium, which is like the flary part attached to the spine. I have a human hip here because that's the one we're the most familiar with. And it's basically if you bump into a table and hit your hip, that is what you're hitting. You're hitting the ilium. And on the next slide, I'll show you what those bones look like on dinosaurs. The ischium is basically if you sit down and you feel bones, that's the ischium. It's the butt. And then the pubis is the front, where all of the organs are held in by, on humans at least. It's very different in pretty much every other animal, but if you're looking for an understanding of where those bones are on a human, that's where they are. And then the final word to really know is the acetabulum, which is the hip socket in dinosaurs. And that's special because it is open and allows for an upright gait compared to, say, for example, the Rauisuchians, which Meg mentioned last time. They have a pillar, they have an erect pillar stance, which means that their hip bones aren't open enough to allow them full motion, and they're stuck being upright. Meanwhile, dinosaurs, some of them, if they really wanted to, could do squats. Humans also somewhat have an acetabulum. It's not nearly like a direct hole through the hip, and I feel like Nick's about to crash into the room and say that I'm super wrong, which is entirely possible. As far as I'm aware, we do have a fairly open hip socket. We don't call it an acetabulum because humans are very different, and humans came up with different words for their anatomy compared to literally everything else on the planet because we're just that special. So that's hip bones. And so the biggest distinction in the different kinds of dinosaurs we have are Ornithischia and Saurischia, which I can't remember if Meg went over it, but I'm going to briefly go over it again. So this might be a review for some of you from last time. So, on the hip bones of dinosaurs. For both of the hip bones, left of the screen is going to be towards their head, right is going to be towards their tail. So the ilium is that thing right along the top that, again, looks like a flare. It surrounds their spinal cord and obscures it from view when you're looking at a dinosaur skeleton from the side. The pubis is the bone that is most forward but beneath the ilium, and then the ischium is the one going back. And the acetabulum is that hole right there, and that's where the femurs go into, and that's where they do their hinge thing and have a lot of motion and are able to stand upright. And that's basically the main distinction between Ornithischia and that's basically a hip bone of a dinosaur. So in Ornithischia, their basal form has a pubis that points towards their tail. Now, it's interesting because Ornithischia is bird-hipped. So at some point in the evolution of birds specifically, and things, and like that's a whole nother argument about what counts as bird or not. But anyways, so in bird evolution, their pubis slowly progressed towards pointing back towards their tail. But in their basal form, which is everything in Saurischia, their pubis points forward instead of backwards towards the tail. It either points down or towards the head of the body instead of towards the tail. And that is going to be your main distinction and main thing that you look at when doing the anatomy of a dinosaur. There are some other features as well, but we're not doing a deep, in-depth paleontology course right now. So hips, that's the main thing. And the main reason why you want to know those other features is if you find a fossil of, say, yet another sauropod vertebra and there's no hip attached to it. Though generally speaking, you can recognize a sauropod vertebra as soon as you see it because they're ginormous as heck. They're like the size of a decent-sized human curled into the fetal position usually. Sometimes larger. So, those are the hips. And now I'm about to talk about all of the Triassic, not all of the Triassic dinosaurs, a lot of the major Triassic dinosaurs that existed during the Triassic. Starting with the Herrerasauridae. So they showed up about 233 million years ago in South America. They are classified as basal Saurischeans, depending on who you ask, but pretty much basal Saurischia, and they may predate the Saurischian-Ornithischian split. They're carnivores. We can imply that from the shape of their teeth. They only have a partially open hip socket, so it's not like a full acetabulum that allows them full motion or allows them a full upright stance, but it's enough in an acetabulum that it's like, oh yeah, this is a dinosaur. They have traits very similar to Theropoda. They have a specific kind of hinged jaw. They have 3 fingers with curved claws, but placed basally due to having no distinct descendants in the fossil record. They're just kind of like they're off standing in their own field during only the Triassic. And on the left here, I have Herrerasaurus. I'm not going to try pronouncing the species name for that. It's too long. I don't want to make a fool of myself. And it's by Green Mamba on DeviantArt. All the art for the dinosaurs, unless I say it's from somewhere else, can be found on A Dinosaur a Day's post about that specific dinosaur. So, that's Herrerasauridae. And into Ornithischians. So the definition of Ornithischia is basically any dinosaur that's more closely related to Iguanodon than to Megalosaurus or Cetiosaurus. Cetiosaurus is a sauropodomorph. So, that's just in terms of relationships. But back before we didn't define things by relationships, what did we define Ornithischians as? So besides having an Ornithischian hip, which I mentioned there as a basal trait, they also had a predentary. A predentary is it's a bone on the lower jaw that kind of looks like a little itty-bitty beak. That's the predentary. You'll see that, the best example I can probably give is when you look at a Triceratops lower jaw, the little beak thing on the bottom jaw looks like a distinct bone from the rest of the lower jaw. It's because it is, and that's the predentary. The jaw hinge on Ornithischians is also lower than tooth level, which is not the case for any of the Saurischeans. So, the jaw hinge is, actually lower than the actual layer, the layers of the teeth in the jaw. And then near the pelvis there's a bunch of ossified tendons, and that is in order to keep that area of the body rigid and together mostly. And those are basically the traits that we had to define Ornithischia before we decided to start defining Ornithischia by relationships instead of traits. And the only example of a Triassic Ornithischian that was definitely an Ornithischian that I could find was Eocursor. And there just honestly aren't a whole lot of definitive Triassic Ornithischians. Most of the dinosaurs that we have from that time period are either basal Saurischeans or Herrerasaurs. So that's basically it. Then I'm going to move on to Eoraptor. Eoraptor was found between 231 to 228 million years ago, and the interesting thing about Eoraptor is that it has heterodont teeth. Heterodont meaning being split up, hetero being different, don't meaning teeth. So saying teeth after heterodont is kind of redundant, except for the fact that heterodont is describing what the teeth are like. So this dinosaur had more than one kind of tooth in its mouth, kind of like humans, because we have incisor teeth, we have canine teeth, and we have molars. A lot of dinosaurs usually just have one kind of teeth. So, for example, analogous to human teeth, a lot of the meat-eating dinosaurs have canines. A lot of the ornithischians have just molars. Sauropods are kind of weird, and their teeth are just weird in general, so that's for a different lecture, though. But generally speaking, a vast majority of the dinosaurs only have one kind of tooth in their mouth. When you have a heterodont, they have more than one kind of tooth in their mouth. So, Eoraptor is traditionally classified as a theropod, but that has been controversial in the past 10 years or so, and it has been placed in Theropoda, it's been placed in Sauropoda, it's been basically placed between Saurischia and Ornithischia, and most recently it's been placed in Ornithoscelida. I don't like Ornithoscelida, but that's for a different lecture. That's just for an entirely different rant. I'm going to deal with that later. And this picture right here is of Eoraptor lunensis by Rebecca Groom. She does a lot of really great paleo art. If you haven't heard of her, she's also paleo plushies. She makes all the really cute paleo plushies. She's just great in general. She does really great art, does really great things. She's a really great human. Okay. Let's see. Is there anything happening in the chat? Aha! Okay, so Sid says, the rock where Eocursa was found was recently redated to be early Jurassic, so we don't have any named Triassic ornithischians anymore. That's good to know. Awesome. So, I'm going to go ahead and put in the lecture notes that this is going to be a just kidding. So that's a note to myself to put just kidding on that slide. So, now I'm going to go on to Saurischians, specifically theropods from the Triassic. So Theropoda, in terms of relationships, is defined as dinosaurs being closer to Megalosaurus than to Iguanodon or Stegosaurus. In terms of traits, theropods have 3 weight-bearing toes on their limbs. They do have a 4th toe, but it doesn't tend to bear any weight. That's why a lot of times when people first start drawing dinosaurs and they forget that 4th toe, people yell at them because it's like, I thought they only had 3 toes. Nope, they have a 4th toe. It just doesn't bear any weight. Among theropods, carnivory seems to be pretty common in its basal members. There hasn't yet been a basal theropod that wasn't a carnivore. And I still messed up a typo on this one, whatever. But so, another basal trait is having bipedal motion. Their forelimbs are reduced to use for other tasks like holding on to prey or grooming or other things they use arms for. Sometimes you just have pinkies for arms, like my favorite friend Majungasaurus. But, you know, the forelimbs are greatly reduced in theropods, which is a big, huge sign that you have a theropod instead of just another dinosaur. Some examples of theropods from the Triassic include Dilophosaurus and Procompsognathus. And then into sauropodomorphs for Saurischians. So, in terms of relationships, sauropodomorpha are dinosaurs more closely related to Stegosaurus than to Iguanodon or to Megalosaurus. Sauropodomorphs are herbivores. There's been no evidence so far of a sauropod that ate meat of any kind. They tend to have a large body size even among the dwarf species. Later on, we'll talk about some of those dwarf species, but even in their environments, they were pretty freaking huge compared to all the other dinosaurs around them. In terms of body shape and body plan, they have long necks, long tails, they have pillar-like limbs, and they have a small head size compared to the rest of their body. They also have very extensive air sacs intruding into their skeleton that can be easily found in a bunch of their bones. This does become a thing later on in theropods, but among sauropods, it's pretty evident early on in the fossil record. Some examples of some sauropods from the late Triassic, early Jurassic are Isanosaurus, Cetad, Plateosaurus, Nambalia, and Pantydraco. I only put Pantydraco in there because I wanted to say the word. Have fun. So, we have quote-unquote, specifically in Sauropodomorpha, we have quote-unquote prosauropods, which means not before the dinosaurs, before the sauropods. Before the sauropods. They are believed to be ancestral to sauropod, and the name for that group of dinosaurs has been shifted to Plesiosauria because Plesiosaurus and related sauropods are very much a thing in the fossil record. Prosauropod is still used pretty colloquially, so when we say prosauropod, it's not because we're inaccurate, but it's because literally a bunch of the PhDs we know say prosauropod as well. Prosauropods have the capacity for bipedal motion as opposed to most of the traditional sauropodas who are pretty rigidly quadrupedal. There is no specific time period for when the prosauropods really showed up or went extinct because several taxa inhabit the prosauropod status. They do have a proposed clade definition, which is all sauropodomorphs more closely related to Plateosaurus than Saltosaurus. Saltosaurus being a titanosaur that exists later on in time. Some prosauropods, most notably Plateosaurus, feature osteoderms, which you can't see in this image of a Plateosaurus because it's been covered in Integumentary Features by Mark Wayton. It's a very cute dinosaur, and I appreciate the fact that its color scheme matches the color scheme of the presentation, but that's because I'm a nerd who enjoys things looking pretty. So, then, we've introduced to you all these dinosaurs, and I'm going to introduce to you the Triassic extinction, which happened at 201.3 million years ago. There are several potential causes for the Triassic extinction. They're all kind of up in the air. The first one is gradual climate change, including sea level fluctuations and pulses of oceanic acidification, which would have caused marine life to go kaput, which would have also influenced how terrestrial life went kaput over time. There's also some discussion of an asteroid impact, but the main problem with that is that there is insufficient evidence for an impact crater of sufficient size to cause an extinction. There's like one line on the Wikipedia article for an asteroid impact that could potentially satisfy this, but it has a citation needed, so I was just kind of like, no. There's no citation there, it's not legit. So, in my personal opinion, but don't take my word as gospel here, I personally am a fan of the volcanism idea. And the reason why I'm a fan of this is because during the time period of the Triassic extinction, Pangaea started to split up into a more distinct sort of two-continent system. And so the Central Atlantic Magmatic Province, which is kind of this area circled in red here, is what split up Pangaea into two separate things. And this was done via rifting, which I explained earlier in plate tectonics, which was just basically the plates are separating via divergence. And this was happening during that same time, and because of that, there was a lot of volcanic material going into the environment and not just being stuck in the crust. So you had a lot of basalt, you had a lot of the gases, you had a lot of CO2. And that definitely could have influenced a lot of things dying during that period. Because as I mentioned earlier, volcanoes usually means death and some amount of ecological change, especially when it's a whole lot of volcanic activity, such as literally tearing apart a continent. This particular drawing was by William Borg, and it's from Wikipedia Commons. I needed to put that notation on there so that I had it properly accredited. It's always good to properly accredit any images you use, unless you've been given permission by somebody else to actually use them. So, the consequences of the Triassic extinction is that 50% of all life was lost, and there was a sudden sharp loss of major marine life during this time. About 48% of marine taxa during this time went extinct. All archosaurs outside of Avametatarsalia and crocodilomorphs go extinct. So all of our Adasaurs, all of our Rhysuchians, all of the fun other archosaurs that didn't eventually become birds or crocodiles are gone. Most of the remaining therapsid stragglers from the Permian extinction also died, except for the ancestors to mammals, and a lot of large amphibians became extinct as well, but they stick around for a little bit longer at least. So, of course, with a bunch of animals dying all over the place and a lot of the really big archosaurs taking up the space suddenly gone, there were more niches for dinosaurs to fill, which they did during the Jurassic, which was from about 201.3 million years ago to 145 million years ago. So, dinosaurs diversified during this time. Much like the other archosaurs of the Triassic, dinosaurs suddenly had a large amount of niches that they could fill. Thanks to luck and competition, those niches were filled by dinosaurs. So, to begin, I'm going to talk about ornithischians. Much like saurischians, there are two main groups of ornithischia that start to develop during this point in time. There's more than like two groups per se, but I'll get to those later. So there's heterodontosaurs, which are basically they're ornithischian dinosaurs, which I explained like earlier. They had more than one type of tooth in their mouth. There's hypsilophodonts. Sorry, that word is really hard for me to do. I'm just kind of like, oh, there's too many words squished into a shorter word. It may be an invalid taxa. I'll talk about that later. Now to the two main groups of ornithischians that start to develop during this point in time. There's the thyreophorans, which we will cover next lecture. Meg will talk about thyreophorans. They start up in the Jurassic with stegosaurids, and then in the Cretaceous, they are the ankylosaurids. Then the second part of the ornithischians that start to jumpstart during this time period are the Neornithischia. They diversify more in the Cretaceous, and they include ornithopods, pachycephalosaurids, and ceratopsians. So, to talk about early Jurassic-specific groups, I'm going to start with Heterodontosauridae, which means different-toothed lizards, and they had 3 different teeth shapes in their mouth. Most dinosaurs only had one type of tooth in their mouth. Heterodontosaurs had, like, things similar to incisors, things similar to canines. The little tusk friend here has a little tusk, and also some molar-like teeth. Not exactly like the ones that we think about, but they had different shapes of teeth in their mouth. They lasted from about 200 to 133 million years ago into the early Cretaceous. They are ornithischian, and they have actually been found with filamentous integument. Specifically, Tianyulong, right here, I drew him, that's why he looks the way he does, was found with filamentous integument. So it's assumed that heterodontosaurs in general had some sort of integument on them, whether they were quills or what have you. They were fairly small. Think of like a small dog. That's how small most heterodontosaurs were. Some were like the size of a beagle instead of the size of like a chihuahua, but they were still pretty freaking small. They are found everywhere except for Australia, because Australia is weird. It's just weird. Australia was pretty far down south during all this time and also broke off pretty early compared to the rest of the continent. So they don't have the same kind of dinosaurs that everyone else has. Like, they still have like the same basic groups, but they're very different. And the next group is the Hypsilophodonts, which is a potentially invalid taxon. It's seen as paraphyletic, which, if you remember from Meg's lecture, basically means that they were like, oh, these and these and these look kind of similar. We're not going to pay too much attention to how they're actually related to each other. We're just going to call them a clade because they look like they belong together. Which, you know, isn't exactly how phylogeny works anymore. Stop that. Let's see. Is there any other notes on here? The don't in Heterodontosaurus and Heterodontosaurus should be pronounced like the don in Iguanodon. I see what you're saying, but also, as we've learned with Meg yesterday, she will say ornithischian, not yesterday, on Monday, she will say ornithischian how she wants to. I will also say dinosaurs how I want to, because honestly, with dinosaur names, half of pronunciation is confidence. If you can say it confidently, you're saying it right. There are very few times in which when you say a dinosaur name wrong, that everyone around you will go, dude, the heck was that? I can't think of any off the top of my head because I say everything right, but that is what it is. Let's see. Yeah, go ahead and ping me for Hypsilophodonts. Yeah, Hypsilophodonts is how you pronounce. Yeah, Hypsilophodonts. I'm not actually past the slide already. I'm sorry, I got caught up in the Discord chat. I'm going to go back to actually talking about Hypsilophodonts. So, technically invalid taxon, they're paraphyletic. They have a kind of wide range that's undefined, mainly because they're probably paraphyletic. So I can't put a specific time range on what exactly fits in there. They're basically basal ornithischians that aren't heterodontosaurids. A good example of this would be Tenontosaurus Tileti by Jose Carlos Cortez, who does a lot of the art on A Dinosaur a Day. He also does a lot of great non-paleo art. He's a pretty chill guy. He's worth saying hello to. I think his, I can't remember his exact Tumblr URL, but he goes by Kets a fair amount of the time. So those are Hypsilophodonts. And I'm going to go ahead and move on to theropods. So theropods are most diverse during the Cretaceous, but we do have some in the Jurassic that are worth mentioning that came from the Triassic. Dilophosaurids continue into the Jurassic, and coelophysids continue to diversify as much as they can because they're very small and very, very basal dinosaurs. Theropods also kind of divide into two groups, starting in the Jurassic and into the Cretaceous. The first group is Tetaneurans, which are defined by having stiff tails. They are discussed later on in the course, so I'm not going to go over them too much. And Ceratosaurs are, and then there are also Ceratosaurs, which are large predators from the Cretaceous, which are also discussed later in the course. So I'm only going to talk about Dilophosaurids and coelophysids in the next couple minutes. So, Dilophosaurids means two-crested lizards. Disclaimer, not every dinosaur in the group has two crests. They're just called Dilophosaurids because that was the first name proposed for the group, and in paleontology, whatever you first name something is the name that it goes by. They existed from about 200 to 188 million years ago, and one defining characteristic of them that exists is having a snout notch. They kind of look like they have an overbite almost, and also like it's an overbite and like a bulbous nose at the same time. It's actually described as being a slot-shaped opening at the base of their nose. And they are large. Like, if you think about the size of a moose and you overestimate that size to get the actual size of a moose, that's how tall Dilophosaurids are. The one in Jurassic Park is actually juvenile. That's canon. You can fight me on that if you don't know Jurassic Park, but I feel like most of you probably know that. They are nothing like what Jurassic Park portrayed them as. They don't have an extra frill. They don't spit poison. They will probably eat you, but you know, they didn't have all the extra features that people like to say they had from Jurassic Park. So, to the right here is Dilophosaurus weatherilli by Sam Stanton, and she does a lot of really cool art as well. She is Artistic Thingum at tumblr.com, and she does a lot of really cool dinosaur art. She does a lot of cool dragon art. She also does an Undertale comic that I really like, but that's besides the point. I'm also just saying that all these artists are really cool and that you should go and find them. A Dinosaur a Day has links to all of these people's art on the posts about these dinosaurs. So if you're interested, go look at that art. So that's Dilophosaurids. And then we have Coelophysidae, and they existed from 220 to 183 million years ago. These guys are really small, they're slender, they eat small reptiles and small bugs, basically. They are very small dogs, like chihuahuas. They're actually the size of chihuahuas. These guys are not to be confused with Coelosauria, which is a clade within Tetaneurans, which I briefly mentioned earlier. So coelophysids, not the same thing as Coelosauria. They're just not. They sound very similar, but they are completely different animals. And to the left here, I have Coelophysis bari by Apsarabis on DeviantArt. They also have art on Tumblr. It's very nice paleo art. I don't know if they posted anything in the recent past. Like, they were really active when I first joined Tumblr in like 2013, but I know that they've become less active over time. But anyways, so Coelophysidae, very small things, very basal and generic. They kind of die out after the mid-Jurassic. And then on to sauropodomorphs. They have the biggest diversity boom during the Jurassic. I mentioned prosauropods earlier, but I'm going to talk about two basal groups that kind of continue on in the early Jurassic. The first one is volcanodons, and they are a proposed family of basal sauropods. They existed from 183 to 175 million years ago. Their only really defining characteristic is having an unusually narrow sacrum, and the sacrum are the bones that fuse the hip bones to the spinal bones. So they have a really narrow one of those. And to the right here, I have Tazodosaurus nami from Dinopedia. So it looks pretty cool. It looks like a ghost. My little ghost friend. Tazu, you ghost. Okay, then Mamenchisaurids. Their name comes from several Chinese words. There's ma for horse, men for gate, and then shi for stream, and together it just means horse, gate, stream, lizard. I presume that these bones were found near a stream that's near a horse gate, and also they kind of look like horses, sort of. They're potentially inclusive of Cetosaurs, which is another group of early Jurassic sauropods. Cetosaurs is where Cetosaurus is, which I've mentioned a couple times earlier in talking about the relationships of where all these dinosaur groups fall and what defines these dinosaur groups by their relationships. Mamenchisaurids kind of start the process of embiggenating, the thing that sauropods do, where they get the longer neck and the larger body in general. They embiggenate starting in the Jurassic. So to the left here, I have Mamenchisaurus, and it's from Dinopedia. Don't know who the artist is. I'm pretty sure I could find out who the artist was, but I was in a rush. So, whatever. And that's pretty much my lecture. I have a review here of what we went over. So we had a basic geology overview, which included the rock cycle, plate tectonics, volcanoes, fossils and taphonomy, stratigraphy and dating, and then I did a basic how to read a scientific paper, and then a brief Langer 2014 review, which was your reading. And then I talked briefly about the weird archosaurs from the Triassic. I talked about the basic dinosaur groups of the Triassic, and also what defines a dinosaur in a group and why, and like how those dinosaur groups were defined. And then I talked about the Triassic extinction, and then I talked about the early Jurassic dinosaur diversification. The last slide here is supposed to be vocab. Again, I had problems with the Twitch stream, and I didn't do the thing where I assembled all the vocab words because I was busy downloading the stuff for Twitch because I'm a fool and didn't realize you needed technology more so than just twitch.tv to do a Twitch stream. But now I know that. And so next time my lecture won't be 30 minutes late. And there we go. So I'm going to go ahead and start my office hours now. If you have any questions about the lecture, feel free to hit me up in the office hours. And if you have any questions about anything else in general, about the class, about geology, feel free to email me or any of the instructors. But if it's specifically about geology, email me because I'm the main geology person in the staff that I'm aware of. And yeah. Oh, so the code word, I was going to have it be one thing, but it's actually going to be Dilophosaurus. That is the code word. This is the code word for today's class is Dilophosaurus. There you go, guys. Okay, guys, you have your code word. So you enter the code word in the quiz that will be put up shortly after this lecture ends. Yes, I said the code word, you guys. Yes, Dilophosaurus. Code is in beginning. So that was the lecture. And I hope you all have a good rest of your Thursday, and I hope you all have a good weekend, and we will see you again on Monday. And yeah, there we go. That's the end of today's lecture. Have a nice weekend, y'all. Bye.